Okay, so we are on part J, I believe, um, of problem number 7. Yeah, we had just done part I. We calculated the 1970 population to be 68.14, and then the actual population is 56.59, so we overshot, we overpredicted. Find the 1970 model error, so that's going to be 56.59 minus the predicted, and then we're going to divide that by the actual, which is 56.59, and multiply it by 100. So we have negative 20.42%. That's our model error. So we have a relatively large model error here. I'm sorry, actually, I got a little bit ahead of myself. I just calculated the percent error. The model error, I did find it. The model error was up here. It's actual minus predicted. That's minus 11.55. I'm sorry about that. But anyways, so model error is minus 11.55. That's actual minus predicted. And then the percent error is what we just found for K. So we did both J and K, and that would be negative 20.42%. Okay. All right, so I would say that our model did not do very well. So for our model error our model did not perform very well in 1970. That's outside of our data set though, so that's the danger in predicting the future. All right, let's move on to number 8. Suppose you're standing on top of a building 475 feet above the ground and you throw a baseball vertically down towards the sidewalk with an initial speed of 37 feet per second. When will the ball hit the sidewalk? So projectile motion equation, our initial velocity is right here, but it's negative, okay, because we are throwing the ball down. So that means our model is going to be, let me just go straight to the calculator with this. Our model is going to be negative 16x squared minus 37x plus 475. So the big thing to remember here is that our initial velocity is negative, and of course our initial position is positive 475. Now if you want to find when the ball hits the sidewalk, let's do a zoom fit here. Terrible picture, but it's still usable. That intersection right there is going to be what we're looking for. So let's do calc 0. Go to the left. My picture's, whoops, got away from me there. My picture is too much. The X domain is too big, but that's okay. It's still usable. Left bound, right bound, and then my intersection point is right there. So hits the ground at 4.414 seconds. All right, let's go to question number 9. We have a 4th degree polynomial function, and we're going to find a bunch of stuff about it. Now, I will tell you in advance, I'm not going to do every part of this because a lot of this will be repetitious, but I'll talk about how you do all of these things. The first thing that we're going to do is enter the function before anything else. So we might as well go ahead and do that. And while I'm doing this, remember, since we have a 4th degree polynomial with a negative leading coefficient, that should tell you some things about kind of what to expect as far as the graph. Okay, if I didn't make any mistakes there. So when I graph this, basically I expect something like that. Okay. Now, I'm going to do a zoom standard, and hopefully this will show me something. And it does. Actually, it shows me a lot. Because you see I had 4 legs there. So that's great. That's exactly what I need. So I think with this picture, I can just do zoom fit without changing anything because I see all of the legs. All right, so there you go. That's a pretty good picture. Now it's a little bit, I might actually want to kind of cut off this bottom portion a bit. I don't need to go to all the way down there, so why don't we go for the Y min. Let's, instead of going to negative 43,000, let's go to negative, oh, I don't know, 10,000 and see what that looks like. So this is just a rough, I'm just kind of roughly approximating what I think will be a reasonable picture. Still a little too much, but usable. Okay, so now let's go to the questions. We want to find the x-intercepts. We want to find the local maxes and mins and domains and ranges. So for the x-intercepts, let's talk about how many we have. So you have 4 of them. 1, 2, 3, 4. So there are 4 x-intercepts. So really, you're just going to have to do this procedure 4 separate times, and that's 4 times of calc 0 to answer this question. So I don't have the patience to do that. I'm sorry, I just don't. But I'll go to calc 0, and I'll just find one of them just to show you. Of course, I screwed that up. I'm going to find this one right here that I happen to be close to. I go to the left of it, I go to the right of it, hit enter, and then guess, and my estimated value is minus 1.5. So one of them is x equal minus 1.5, and then there are 3 more which you can find, and the answers are at the end of the document. Okay, let's move on to the mins and maxes, which is B through D. The first one says the graph of f has a local maximum near x equal negative 5. Which indeed it does. That's it right there. So to find that, we would go to calc maximum, and you just scroll over, and my calculator keeps wanting to run away from me. I go to the left of that maximum, and if you can't see what you're doing, you can always make your window higher. So I could make this like 7,000 and then graph it, and I'll have a little more vertical, headroom up there to work with. That's just me being a bit persnickety in my picture. So again, I was trying to find my maximum. So we go over here, and now the function's not in the way, so I can actually see what I'm doing. Left bound, right bound, and my guess is somewhere around there. And so I'll find that local maximum right there is those stated values. That's the coordinates, the x and the y coordinate. Negative 4.994 and 5,082. Okay. For part C and D, once again, I'm going to let y'all finish those. It's the same sort of thing. We use calc minimum and calc maximum in the same fashion. Okay. Let's move on to parts E and F. So what's the domain of F? Well, this you should be able to immediately answer. It's a 4th degree polynomial with no restrictions because this is not a word problem. So its domain is all real numbers. For the range, since it's opening downwards, and I know that because, well, I'm looking at it, but it also has that negative leading coefficient. So the range is going to be from negative infinity up to, actually, it's whatever the absolute max y value is, which I believe we found it already. It's that. So up to 5,082. Now I just happened to have found the absolute max. It could have been over here or something, but clearly this is the high point. So that's 5,082. So negative infinity up to 5,082.3, I think it was. That's a bracket. 0.03, sorry. Being a little sloppy. There we go. So that's our range. And our domain. Okay, moving on to where it's increasing and decreasing. So once again, to actually do this, I need to, really, here's what we have. I've got a function that looks like this. And so this thing, where it's increasing, is going to be the x values that go from here to here, and the x values that go from here to here. So that's going to be from negative infinity up to that x coordinate of the maximum, which we actually know to be negative 4.99, and then union, and notice that's the x coordinate, and union, and then here I need to put whatever that x coordinate is up to that x coordinate, which I was too lazy to find, but it's going to be that minimum value, that x coordinate minimum, and that maximum. So let's cheat. Let's go to the answers just to interpret what it is we're looking at here. So this is G on number 9. So for number 9G, it says 0.71 to 4.85 is the other part of this interval. So what this is saying is that this value right here, its x coordinate is 0.71. I don't know what the y coordinate is. It's something. But then the x coordinate of this point is, of course, I've forgotten it already, is 4.85. So that's 4.85, and then whatever that maximum is. And so that's going to be from 0.71 to 4.85. That would be our other interval where the function's decreasing. Now where is it? I'm sorry, where it's increasing. So where is it decreasing? Well, everywhere else. So it's going to be decreasing here and here, which again is going to be x coordinate intervals. So that's going to be from minus 4.99 up to 0.71 union 4.85 up to positive infinity. That's where it's decreasing. So this region here to that. And as you can see, where we're increasing and decreasing is very much connected to the turning points of the function. So you need to know those turning points to actually state these. Okay. All right, let's see if we can finish this off. So what else have we got? How many solutions does the equation f of x equals 500 have? Well, I need to go to the calculator for that. I'll put in 500, and I'm just going to graph this and then count it. How many times does that line intersect? So it's a little hard to see, but it basically here, 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 so everywhere it could. So it intersected 4 times, so we will have 4 solutions. 4 solutions. Question J goes a bit deeper. It says find the positive values for which f of x equals 500. So are there any? Well, yes, there are 2 of them. I think I'm going to need to zoom in. To see that a bit better. Hopefully that'll give me an okay picture. But so now, since these are my positive x values that I'm looking at, I need to find this intersection and this intersection. So we're going to have to do calc intersect twice. And the first one is 3.714, and then we do it again. And I may run out of time here, so I think I am going to run out of time. But basically, you just repeat this procedure, but make sure to move your cursor over to the other intersection, and so you should get the stated value that's in the solutions. And that is going to finish off the Unit 4 practice problem set. Okay.